to prove that the alternating group is abelian if and only if n is less than or equal to 3, most of you chose a strategy for the forward direction that uses a contrapositive, which would say assume n is greater than 3, and then we want to show an is not abelian. And so what was the key to that argument? I think Cam, you just alluded to it. The key observation is that if we can prove A4 is not abelian, right? If we know A4 is not abelian, A4 is a subgroup of A5. And every subgroup of an abelian group we know is going to be abelian. And so if I have a non-abelian subgroup, then that means that the parent group is not abelian by the contrapositive, right? So as soon as I have A4 not abelian, I know that all the rest of the alternating groups are not abelian. So how did we prove that A4 was not abelian? Show it. We can show it pretty constructively and precisely, right? Give me an example of two elements in this group that don't commute. What were they?
1, 2, 3, 1, 3, 4.
Sure. 1, 2, 3, 1, 3, 4. So the key here is to get two elements that are both alternating group elements. So they have to be even permutations. But we also want them not to commute, and so we don't want them to be disjoint of one another, right? Because if they're disjoint, they will commute. And A4 is the smallest alternating group in which we can make this happen. A product of two non-disjoint even permutations will not commute. You can check that sigma tau is, well, let's see. 1's going to go to 3, and then 3 is going to go to 1. So 1 is actually going to end up in the same spot as it started. I'll write that way. 2 is going to stay put and then go to 3. 3 is going to go to 4, which is then going to stay put. So I think this is what you get when you do sigma tau. You may want to check me on that. Meanwhile, tau sigma. So there, 1 is going to go to 2 and then stay put. 2 is going to go to 3, which then goes to 4. And then 3, I believe, stays put. But anyway, the key observation is that these two are not equal to one another. Right? Sigma tau is not the same as tau sigma, and thus A4 is not abelian.
Can you explain how 3 stays put?
Yeah, let me double check myself there. So 3, so if I'm doing this permutation, it means sigma is acting first, and in sigma 3 goes to 1, and then tau is happening, and so 1 goes to 3. And so at the end of the day, 3 has gone back to 3. So that did work out. Thus, A4 is not abelian, and thus, AN is not abelian since A4 is a subgroup. Since A4 is a subgroup of AN. Right? So there's the proof of the forward direction. Right? As soon as n is greater than or equal to 4, AN is not abelian. What's the proof for the other direction? Why is AN abelian for n less than or equal to 3? What does A3 look like?
Identity 1, 2, 3, 1, 3, 2.
Yeah, we can explicitly list out all the elements in A3. And since A1 and A2 are both subgroups of A3, that means that they must live in here as well. Well, now why is this abelian?
Because you have the identity which commutes with everything and
Uh-huh.
a set of inverses, so they commute with each other.
Yeah. This identity commutes with everything. And then these two elements are one another's inverses. And therefore, they're going to commute with each other. Inverses of each other, therefore commute. Yeah, that's a very elegant way to argue this, right? To show that a group is abelian, we need to show that the center of the group is the entire group, or another way to say it is that the centralizer of every element is the whole group. And this argument does that. Identity always commutes with everything. And these two elements, because they're one another's inverses, they commute with one another, and therefore also with everything, because the identity is also there. So A3 is abelian, but then A1 and A2, what do we know about them?
They're subgroups of A3.
They're subgroups of A3. And if A3 is abelian, that means
They must also be abelian.
they must be abelian. Great. I mean, these were both the cocktail napkin versions of these proofs, but those are the insights that give us what we need here. Right? So when we look at the alternating groups starting from the smallest A1 and then going A2, A3, A4, A5, the abelian switch shuts off at A4 and then remains off for every alternating group acting on 4 or more symbols. Meanwhile, for the symmetric groups, the abelian switch actually turns off sooner, right? It turns off at S3. S1 is abelian, S2 is abelian, S3 no longer abelian, and therefore all the higher symmetric groups also no longer abelian. In the symmetric group on 6 symbols, we didn't get any elements whose order was more than 6. Right? All the orders are 1, 2, 3, 4, 5, and 6. Which can lead you to think that in Sn or in An, we can never have elements of order bigger than n. But here, this is asking me to show that that's not true. Right? That in A10, we have an element whose order is bigger than 10, order 15. So how do we make an element of order 15 inside of the alternating group A10?
Can I give you a brute force calculator version?
Okay, yeah. What's the brute force version?
Well, so we know that if we do S10, the order of S10 is 10 factorial.
The order of S10 is 10 factorial, 3, 6, 2, 8, 8, 0, 0. Okay.
Holy crap. All right. And then A10 is half of that.
The order of A10 is half of that. That's going to be 1, 8, 1, 4, 4. Oh, come on. You can divide that number by 2 in your head, right? Okay.
And then, because he made the question, he knows what the order would be. And then you can divide the order of A10 by 15. If it divides it evenly, then that number is like the element that can...
Thus, there exists an element of order 15. Okay, somebody, all right, this, I like brute force. I like brute force. Somebody tell me what this explanation is missing. No, I think, you've suggested your conclusion. Aha! So, Pin has made an observation back here. What kinds of groups would we be on firm footing making this assertion? If the group is cyclic, we know that every divisor of the order of the group will be represented as the order of one of the elements in that group. So this argument would be awesome if A10 were a cyclic group.
We know...
Is A10 a cyclic group?
Not necessarily.
Got you.
Better than not necessarily? Definitely not. Why not?
Because A4 contains elements that are non-commutative.
And?
Or is a subset of anything greater.
We just proved that.
Yes. A10 is not cyclic because it's not abelian, right? And every cyclic group has to be abelian. Right? Every cyclic group is abelian. So we can't necessarily use this line of reasoning.
The original number you get still work. It won't work because, when we did like the...
14 from. If this argument doesn't work,
Find 2 cycles that apply to the LC.
yeah, there we go. So here's the occasion to use the order formula. The order formula, remember, let me get that on the board.
I'll take the...
No, this is a subtle point, right? So remember this order formula? If I have 2 disjoint cycles, then the order of their composition is the least common multiple of their orders. So yeah, if I can have an element in A10 which is a product of a cycle of length 3 with a cycle of length 5, then I'll be all set. But the question is such an element going to be an element of A10? How do we know?
Because we can yes.
Say again, sorry.
You can put it with 2 identities.
With 2 identities like this?
Yeah.
One cycle, one cycle. Okay, fine. But why does it belong to A10? It's a permutation of 10 elements, but why is it in the alternating group on 10 symbols? What kind of permutation does it have to be? Well, how do we know it's an even permutation?
Because 3 minus 1 is 2 and 5 minus 1 is 4.
Yes. So if I expressed it as a product of transpositions, I'd get 2 transpositions from over here, 4 transpositions from over there, and then these couple of fake ones from the end. They're not actually. I shouldn't even write that there because they're not transpositions or identities. So how many total do I have? 6. So this belongs to A10. So not only have we shown that there exists an element of order 15, we've found an element of order 15 inside of A10.
What is the element? It's just these random numbers that you put in there?
It's this permutation. It's this composition of 2 cycles, right? I've noticed this also walking around that we've done so much working with cycles that people are confusing the entries in cycles with elements in the group. The elements of these groups are permutations, which are written and represented as products of cycles. But the cycles themselves contain these entries in them that are not elements of the group. They're just the positions. They show what happens to the positions when we permute them.